Hello.
Good evening, ma'am.
Good evening. Are you able to see the screen? Is it
Yes,
sharing
ma'am.
with you? Okay.
Yes, ma'am.
See, in the last class, let's just do a quick revision of the topics which we did. We did elasticity, property of a body which tends to regain its original shape and size. And then we saw two types of bodies again. First one was the perfectly elastic body, where the body regain its shape, and perfectly inelastic, which does not have the tendency to regain its shape. Then after seeing the types of deformation, we covered the topic stress. So stress is external force acting per unit area, force per unit area. And there were two types of stresses, normal stress or longitudinal stress, when the force was applied normally or perpendicular to the surface. If the length increased, that was tensile. If it decreased, that was compressive. And if the force is applied parallel to the surface, then that corresponding stress is tangential stress. We also discussed strain, right?
Yes, ma'am.
Yes. See, strain was change in dimension
By original.
by original dimension. Change in dimension by original dimension, right? And then we saw other three types of strain. If there was a change in length, then that corresponding strain was longitudinal strain. And if there was if the deforming force produced change in volume alone, then that type of strain was, what was it? Volumetric. Right?
Volumetric. Yeah.
Just try to remember it from the name itself. And if this deforming force produces change in the shape of the body, then that respective corresponding strain is shearing strain.
Strain.
All right. See,
Yes, ma'am.
on the removal of the deforming force, an elastic body will regain its original state only if the condition is that only if the deforming force does not exceed a certain limit. So that maximum stress from which an elastic body will be able to recover its original shape when that particular deforming force has been removed. That maximum stress is known as elastic limit. All right. So
Yes,
the maximum stress from which an elastic body will recover its original state after the removal of deforming force is called elastic limit. Now see, we have Hooke's law here over here. So within elastic limit means the body has not, see, if the body exceeds its elastic limit, for example, if I say load is suspended from a copper wire, right? If a load is suspended from a copper wire, it is found that the wire does not regain its original length after the removal of that particular load. Then it means the wire has exceeded its elastic limit. All right. So
yes,
within elastic limit, if the elastic limit is not exceeded, has not been exceeded, then force is directly proportional to the extension. Or we can say the extension produced is directly proportional to the applied force. For example, if I'm having this wire of length L, now the length has increased to some L dash. L dash. Fine. So I would say this extension produced, let's say X, is proportional to the force which has been applied. This is Hooke's law. Now what happens in here? Now see, within elastic limit, it is said that the strain produced in an elastic body is directly proportional to stress. So you can relate it to this which I have written.
yes, ma'am.
This force is directly proportional to extension. So if we measure the deforming force, so we'll say stress is a measure of the deforming force and strain is a measure of the distortion produced or the deformation. So stress is directly proportional to strain within elastic limits. Within elastic limits, stress is directly proportional to strain. Now, using your basic mathematics, how do we remove the proportionality sign? we put an equal to sign with a constant, right or wrong?
Yes,
This
ma'am.
is how we, yes. So now if I take this quantity in the denominator side on the left hand side, so this would be stress divided by strain, gives me a constant. Yes. So
Yes, ma'am.
this constant that I'm getting on dividing stress to strain, this constant is known as modulus of elasticity. All right. So stress
Yes,
is
ma'am.
directly proportional to strain within elastic limits. And when we remove this proportionality sign, we get a constant, which is the ratio of stress to strain. That physical quantity is known as modulus of elasticity. All right. So its value
Yes, ma'am.
depends upon the material and on the type of deformation involved. Okay, you note this down, then we'll move forward.
Okay, ma'am. Completed, ma'am.
All right. See, it's written over here. I've written it for you. Greater is the modulus of elasticity of a material. Harder is it to change its size or shape or vice versa. See, now let us see the SI unit of modulus of elasticity. So since let us represent this constant or modulus of elasticity by E. At EV, the constant that we are getting on dividing stress to strain. Modulus of elasticity. So if E is the ratio of stress to strain, do you remember what is the SI unit of stress? Just try to recall.
Newton per meter
Square, Newton per meter square. See, stress is force per unit area, means force divided by area. So force is Newton, area is meter square. So it's Newton per meter square. So the SI unit of stress is Newton per meter square. And can you remember what is the SI unit of strain?
Strain doesn't has any unit. It's
Exactly, it's a
dimension.
dimensionless quantity. Yes. See, because it's change in dimension to the original dimension. So both dimensions are same on the numerator as well as on the denominator. So it's a dimensionless quantity and it has no unit. So now can you tell me what can be the SI unit of modulus of elasticity?
Newton per meter square.
Exactly, since this has no unit stress. So SI unit would be Newton per meter square, or I even told you in the first class, 1 Newton per meter square is equal to 1 Pascal. Yes, so you can say 1 Pascal. Fine. Now see, if we plot the graph, between strain and stress, can you tell me what should be the nature of the graph? See, both the quantities are proportional to each other. So it should be a straight line.
Yes, ma'am.
Stress and strain both are proportional to each other. So the graph of these would give us a straight line. So let's say this angle is theta. Okay. If I take tan theta from this, tan theta is perpendicular upon base.
Yes, ma'am.
So perpendicular is y-axis. That is strain. So tan theta is strain divided by base. Base is our x-axis. This is our base. So this gives me stress. And tan theta is the slope of the graph. It's the slope of this graph. So tan theta is stress by strain and strain by stress, and strain by stress is 1 by E, means one reciprocal of modulus of elasticity. Yes.
Yes, ma'am.
Strain by stress. This is the slope of the graph. Now see, if we plot a second graph between stress and strain. Now see, again, it would be a straight line because both are proportional to each other. But now if we take out the slope, if we calculate the slope, again, the slope would be equal to tan theta. And tan theta now is the perpendicular quantity, means the y-axis is now stress. And the base is our x-axis again, that is strain. So in this case, we are getting E. That is modulus of elasticity. Fine?
Yes, ma'am.
All right. So if you plot strain on y-axis, then you get 1 by, and if you plot stress on the y-axis, then you get
E.
exactly. Now, see, since there wasn't a single type of solid deformation. There were three types of deformation. Then we had various types of stresses. Then because of the various types of stresses, we had different types of strain. So similarly, since E or modulus of elasticity, the ratio of stress and strain, we don't have a single type of modulus of elasticity. So one you might have heard of Young's modulus,
Yes, ma'am.
Young's modulus of elasticity. Then one we have bulk modulus of elasticity. And another we have modulus of rigidity. Rigidity. Now we'll discuss each of these and we'll start with Young's modulus. First, you just note this portion and then I'll scroll it down when we're done.
Okay, ma'am. Done, ma'am.
Note these down as well. Young's modulus of elasticity comes into action when there is a change in length. And bulk modulus of elasticity comes into action when there is a change in volume. And modulus of rigidity comes when there's a change in the shape. Note this, then we'll begin with the first one, Young's modulus.
Okay, ma'am. Done, ma'am.
See, let's start with Young's modulus. Young's modulus is, see, modulus of elasticity is the ratio between stress and strain. So this particular type, Young's modulus of elasticity, this is the ratio of longitudinal stress to the longitudinal strain. And it's mostly represented by a capital Y. So this is normal stress. You can say normal stress or longitudinal stress. Normal stress to the longitudinal strain. To the longitudinal strain. So if you remember, longitudinal strain was a change in length. When there was a change, when the deforming force produced a change in length. And normal stress was that type of stress when the deforming force was applied perpendicular to the surface, normal to the surface. So that was normal stress. Normal stress is, I'm giving you an example over here, just like this. See, this is a wire. Its original length is L. And it has a cross-section area. Wires are cylindrical. So if you look at it from the interior view, they form a circle and they have a cross-section area. Yes. So let that area be A. That cross-sectional area is A. So L is the original length of the wire. original length of the wire. And A is the area of cross section. Area of cross section. Now I have applied a force, making an angle of 90 degrees. That perpendicular deforming force I have applied, and it has gained its length. Let's say this extension produced this much portion which has been extended, let it be L. So F is our deforming force. And delta L is the extension produced, or we can say change in length. Zoha, is it clear till here?
Yes. Yes, ma'am.
Okay. Now I want to know from you, by looking at the figure, can you tell me what is the normal stress over here?
Normal.
How do we write the formula of stress? Just recall, you'll be able to learn it right now only.
F by A.
Exactly. F by A. So normal stress or the perpendicular force which has been applied. So this would be F by A, the deforming force per unit area of the cross section. Now, can you again look in the figure and tell me what is the longitudinal strain produced? Just try to recall the formula for strain, longitudinal strain.
Delta L
See,
by L.
delta L by L, exactly. Change in length divided by original length. So this would be delta L divided by L. Now our modulus of elasticity was the ratio of normal stress and longitudinal stress. So it
Yes,
would
ma'am.
be the ratio of these, F by A, the ratio of normal stress, this whole term is the normal stress, to the
Delta L.
longitudinal strain. So we can write the formula as FL A divided by delta L. And since it's again the modulus of elasticity, so the SI unit, as we have discussed it in the previous section only, it would be Newton per meter square or Pascal. Is it fine?
Yes, ma'am.
All right. See, Young's modulus, since modulus of elasticity depends on material, it's a material property. So we have different values of Young's modulus for every substance. For example, for steel, it is 20 into 10 to the power 10. For glass, it is 7 into 10 to the power 10. For brass, it's different. For aluminium, it's different. Fine. Just
Yes,
note this down. We'll begin with the numerical part.
okay, ma'am.
Note this and tell me, I'll scroll it for you.
Sure, ma'am. Done, ma'am.
You note it down. Meanwhile, I'm writing a numerical. Then you just try that numerical, then I'll help you.
Okay, ma'am.
See, the question says that a composite wire of uniform diameter consists of a copper wire of length 2.2 meter and a steel wire of length 1.6 meter. Means after at the terminal portion of the copper wire is attached the steel wire. Means it's a single wire case. Now these wires are loaded by some weight. That weight you have to calculate. What is that common weight for them? The Young's modulus for both have been given. Just try it once. Have you noted this portion, the above
Yes.
theory
Yes,
portion?
ma'am.
Okay, okay. I'll just give you a brief of the question again. Just try it yourself. See, let's say this is a copper wire. It has a thickness. This is a copper wire. Its length is given 2.2 meters. This is the copper wire. Yeah. Then we have within this only, in the continuation of it, we have a steel wire. This is the steel wire. This length is given to us as 1.6 meters. Fine.
Yes, ma'am.
Now there's a force, let's say F or any weight has been applied to this. You have to find out this weight. Okay.
Yes.
And remember, they have the same area of cross section.
So, like, ma'am, I'm supposed to add both the lengths.
Yes.
I'm
Sorry,
supposed
what
to
did you say?
I'm supposed to add like the copper and the steel wires length.
Yes, yes. See, I'll give you a hint. Just do this. Write the Young's modulus formula for copper first. Then write the Young's modulus formula for steel wire. You will get two formulas. You will get two equations. Area will be eliminated because the area of cross section is same. Then you will be able to figure it out better.
Okay, ma'am. Ma'am, is it 2.5?
No. See. This portion, what is written is as 0.7 millimeter, is the total extension produced. Means we don't have that specific extension or change in length for copper and steel written. So change in length for copper plus change in length for steel, this total value is 0.7 millimeter given. And don't forget to convert all these millimeters into meter because we have to find the answer in SI. This is steel. So delta L copper plus delta L steel is given this. You write the formula for Young's modulus formula for copper. You write the Young's modulus formula for steel. In this portion, area and delta L. This would be our variables. Area would get cancelled in both the equations, and force will also get cancelled because the force and the area of cross section is same. So once you get the value of delta L of copper and delta L of steel, then you can put it in any of the equations and get the value of that particular force or weight we are searching for. Fine.
Yes, ma'am.
Just try this. I'll help you out.
Yeah.
See, Zoha, it's actually a lengthy question, so you can calculate it later on. I'll help you. I'll tell you the steps. How do we have to do this?
Yes, ma'am.
I'm reading the question again. Just try to learn it. A composite wire of uniform diameter 3 millimeter. Uniform diameter means the cross-sectional area of copper is equal to the cross-sectional area of steel, and the cross-sectional area of this common wire is not the area, the diameter is 3 millimeter. Now it consists of copper wire of this much length and a steel wire of this much length. And it is stretched under a load. Let's say, let that force be F. We have taken that force F by 0.7 millimeter. It means that copper wire must have stretched to some amount and the steel wire would have stretched to some amount that we are not aware of because it is not mentioned in the question. The question is demanding the force. So see, delta L copper plus delta L steel means the change in length of copper plus change in length of steel. The total change in length or the extension produced is 0.7 millimeter, or we can write 0.7 into 10 to the power minus 3 meters. Now Young's modulus for copper and steel are already mentioned in the question. So for copper it would be, let that force be F because we are not aware of, and let us take area as A only right now. Length LCU means length of copper wire. This LCU is this given 2.2 meters divided by delta LCU. Yes.
Yes, ma'am.
Similarly, we have it for steel. F by A, L for steel, and delta L S. I'm just writing S for steel. So these are the two equations here. Now let's put the values then. Or let us take the ratio first. If you take the ratios of them, 1 and these two, means you divide 1 and 2. So this would be Young's modulus of copper, 2 Young's modulus of steel equals to force by area LCU by delta LCU. This is for this whole term, copper term. Now, since Young's modulus of steel is in the denominator, the whole term will get reciprocal for it. So A delta LS by F L steel. Till here, is it clear?
Yes, ma'am.
So now the force will get cancelled, area will get cancelled. Now see, we are getting two equations. We know the rest of the values. We know the value for LS, we know the value for LCU. We know the value for YCU and YS. What we don't know is delta LCU and delta LS. So this will form one equation, and another equation we already have, which is mentioned in the question. This, the delta LCU plus delta LS is 0.7. So let us put the values. So this would be 1.1 into 10 to the power 11 divided by 2 into 10 to the power 11 is equal to 2.2 into delta LS, means change in length of steel, divided by 1.6 into delta LCU. Now on solving this, we will get, you just solve it after the class. You will be getting, just match it with this, 0.4 LCU is equal to delta LS, means delta L. Now this is the first equation. This is another equation we have to solve it. This is our equation, and another equation that we have is LCU plus delta LCU plus delta LS is equal to 7 into 10 to the power minus 4 meters. So, two equations, two variables. Will we be able to find the value of delta LCU and delta LS from the data? Is it sufficient now?
Yes,
Two
ma'am.
equations and two variables. Now what you have to do? You have to put any of the values. Now once you have the value of delta CU, so what you can do? See, in this equation, in this portion, only delta LCU was unknown. Otherwise, what is the area of the cross section? Pi r square, and radius you already have since you have the diameter. So I'll tell you. On solving these equations, you will be getting value of delta del CU as 0.5 into 10 to the power minus 3 meters, and delta L steel as 0.2 into 10 to the power minus 3 meters. Once you solve these two equations. using your basic mathematics. It's not tough. Fine.
Yes.
So the value of Young's modulus was for, let's say, copper. Let us take for copper was F by A LCU divided by delta LCU. Now, what was the Young's modulus for copper? 1.1 into 10 to the power 11. Force we have to find out. Length of copper wire was also given 2.2 meters. For area of cross section, we have pi r square. Now see, diameter is 3 millimeters. So radius would be 3 by 2 millimeters, means 1.5 millimeters. So this is 1.5 into 10 to the power minus 3 meters. Yes?
Yes.
So pi r square. R square is square of this whole term into delta LCU. Now we have already calculated the value of delta LCU. 0.5 into 10 to the power minus 3. Now this is just a single equation with a single variable f. Pi value is 3.14 as you already know. This is how we had to calculate. Is it fast or shall I repeat once more?
It's clear, ma'am.
It's clear? On solving this, you will get the value of force around 176.8 Newton. Just try this question when the class is done. All right, note this
Yes,
down.
ma'am, can you please scroll down? Then, ma'am.
Okay, see, the time is not left much, so I'm giving you a question. You just try this. We'll discuss that question in the next class.
Sure, ma'am.
Just note this.
Yes, ma'am.